All right, let me continue. And now I'm moving into the section of the test where it talked a lot about whether something had a removable or non-removable discontinuity. Okay, so let me go ahead and take a look at all of these. This caused more problem than I expected. All right, so on 14 on one version, we had this problem. Okay. And then let me do the piecewise from the other. And then every version had a rational expression, a piecewise, and then another one. So this was number 16 on one version, and then the piecewise was number 15 on the other. Okay. Okay. All right, so let's look at these two. Both of these have trouble spots, have discontinuities. All right, so when you look at 14 on both versions, you had something similar to this. So the key was for you to get the expression factored. So the numerator was x minus 9, x plus 9. The denominator, write that a little better. Okay. The denominator could factor into x and x, probably 9 and 4, since we're trying to probably cancel something out. And the 9 would need to be positive in order to get a positive 5x there in the middle. So when you're looking at rational expressions, it's only the denominator that causes discontinuities. So there are discontinuities at x equals negative 9 and at x equals 4. There is not a discontinuity at x equals 9. See, this factor in the numerator, that would give you where the function turns out to be 0. That would give you a 0 of the function, not a place where the function is undefined. The problem with discontinuities are trouble spots you might have. And so, for instance, this right here can't be 0, the denominator. Okay? But there's two types of problems. At x equal negative 9, we would have just a hole. It's a removable discontinuity. We can just cancel out that x plus 9 factor. But at x equal 4, we would have a vertical asymptote when they later ask us about that. You can't fix that problem. That's a non-removable discontinuity. Okay. All right, so on any rational function, it's the denominator that is where you could have trouble spots where the function is not defined. That's where you have points of discontinuity, and they might be a big problem like they are with a vertical asymptote, like non-removable. You can't fix that situation, or they might just be little bitty holes, which you can fix. So you can still find the limit as x approaches negative 9, but you would have a limit going to either positive or negative infinity at x equals 4. Okay? Now, 16 on one version, and that was number 15 on the other. On other version. Okay, this you had a homework problem that related to this as well. The problem here is right here. When x is coming towards 3 from either the left or the right, if you were coming from the left, okay, that top rule can only be used when x, okay, so when x is less than 3, the top rule is used. When x is greater than 3 coming towards it, you would use the bottom rule, okay? So the reason there's a point of discontinuity there is if I tested the top one and put a 3 in, I would get 1. Okay, let me erase that. Okay, I shouldn't use that. If I were being asked to find the value of the function at 3, I should use the bottom rule. But I'm trying to see if there's a space in between the y values or not. So I'm plugging in 3 into the top rule and plugging 3 into the bottom rule. And I know the output is 1 on the top rule and 4 on the bottom rule. So what that means is at 3, let me see if I can draw it a little better. I need to move over to do it. So that means at 3, see this top rule at 3 would have a value of 1, okay? So let me get the y-axis in there. So it would have a value of 1. The bottom rule would have had a value of 4. Okay, let me make that a little shorter. Okay. So one rule, you would have had a value of 1 at 3. With the other rule, you would have had a value of 4 at 3. Okay. So it's a piecewise function. The 2x minus 5 one, that would wind up being a line that would do something like this. Okay, you didn't need to know how to graph it. You just needed to understand that critical spot right there was what you needed to worry about. Okay, and then the x plus 1 rule would have been something like that. And it's defined here, and it's an open circle there. But the thing was, they weren't overlapping. You didn't have the same value there. So it actually, you would have to lift your pencil in order to draw it. So that's at 3. So at x equals 3, there is a non-removable discontinuity. Okay. All right, and then there was one more problem. Okay. Let me see if I can get a little more paper before I go on. Right, number 15 on one and 16 on the other. Okay, it was something like this, where you had an algebraic function and then you had a trig function. And on one version it was cosine, on the other version it was sine. But everybody should know that sine and cosine just look like that. They're nice and continuous. 3x has no trouble spots. There's no denominator. There's no radical. So that's just continuous everywhere. So the whole thing is continuous everywhere. No trouble spots. Has to do with domain of the function. Okay. There's no trouble spots on either of those. Okay. All right. And then there was a related question that just asked you to find the vertical asymptotes and to write the answer in equation form. So it's really using the language from the homework. So number 17 and 18, they looked like this. This was on one version. One of the problems on one version looked like this. And let me take the problem off the other version. Look like this. So this is related to what just happened in the previous one. Okay. And this was X over, yep. And these were just called F. Okay, so you had two questions. They were like this. They might, on one version, the other one was first and had slightly different numbers. But this one was 17 and 18. And it was asking you to find the vertical asymptotes. And I was assuming you would use your pre-calculus skills on it and not really have to go in and do limits to prove that they're asymptotes if you understand the whole pre-calculus part of factoring these. Okay. And then noticing again that you have two trouble spots, one at 0 and one at a -1. Both of those would cause the function to be undefined. But you can remove this problem and get just 1 over x plus 1. So -1 at x equal -1, you have a non-removable discontinuity. Okay. If you did the limit as x approached -1, okay, if you did the limit as x approached -1, it turns out to be a vertical asymptote. Like you could prove it to me. Turns out to be a vertical asymptote because if you did the limit as x approached -1 from the left, did the limit as x approached -1 from the right, you would get positive infinity on one of them and negative infinity on the other in this case. Or they would, they have to both go to infinity of some sort in order to be a vertical asymptote. But I really wasn't expecting you to have to go on and analyze that because you already know it's a vertical asymptote from your pre-calculus skills. And you already know you have a vertical asymptote at, and the equation would be x equals -1, thinking of it as a vertical line. See, the definition of a vertical asymptote has to do with if you imagine approaching -1 from the left and from the right. Okay, if it goes towards infinity, then you have a vertical asymptote. So to the left of -1 would be -2. If we approach this from the left, see, I know at -1, I'd have 1 over 0. So I know it's an infinity of some sort. If I approach -1 from the left, what you want to do is you want to test, okay, so what happens if I come from the left of -1? If I come from like -1.5, see how I'd have a positive over a negative? Okay, see, I know it's going towards an infinity of some sort. I just need to decide which one. And so what I'm noticing is when I plug in -1.5, which is like coming to -1 from the left, I get a positive over a negative. So that's going to be negative infinity. And then I can look at it coming from the right of -1, coming from 0 towards -1. So imagine plugging in like -0.5. See how that would be a positive over a positive. You still have the infinity situation, okay? You just have to decide, is it positive or negative infinity? So this one would be positive infinity, okay? All right, so that whole discussion right there, I would let you not do because with pre-calculus techniques, we know at x equals 0, we have a hole. And at x equals -1, we have a trouble spot that's non-removable. So that gives us a vertical asymptote. Okay, so let's just use that idea here. When we factor the numerator, we get x, 7 and 6 has to be +7 and -6 to get the middle term of 1. The denominator factors into x plus 6, x minus 6. So the x minus 6 factor we can cancel out. We do not have a vertical asymptote at 6. We have a hole. So at x equals -6, we have a vertical asymptote. And the equation for it would be this. The line where all the x's are -6. Okay. All right, now let me go into the problems after that. Okay. Come on. Okay, finally. Let me go ahead and do that chunk of problems. Now in 19 through 24, okay, you have those problems that many of them might turn out to be infinities, but they don't have to be, but you're doing one-sided limits. Okay, so 19 through 24, we're dealing with one-sided limits. They can turn out to be just numbers, but they might turn out to be either positive or negative infinity. Okay. All right, so let's go ahead and just do several of these. So let's look at number 19. On one version, I had you coming from the left. On the other, I had you coming from the right of 4. So let's just pick one of those. Okay. So first off, you can tell you have an infinity situation because if you plugged in 4 using direct substitution, you would get 4 over 0. So you have to analyze. You're never going to be right at 4. You're approaching x of 4. You're approaching it from the left. So what you need to find out is as you're coming to 0, is it a negative on its way to 0 or is it positive? See, any number, any constant, when you divide by 0, that causes that expression right there to blow up either towards positive or towards negative infinity, depending upon what's going on as you approach that critical number. Okay, so what you ought to be thinking is, I'm approaching 4 from the left, so from 3, going this way. So you know it's an infinity. You're just trying to decide the positive or negative on this one. So you can come in maybe and just try like 3.5 over 4 minus 3.5. Okay. If I put in a 3.5, I would have a positive on top and a positive on the bottom. Now you see you're going to be getting closer and closer to 4, so you're going to do 3.9, 3.99 and all, but every time you're going to be positive over positive. So this one would have been approaching a positive infinity. Now the version that had the x approaching 4 from the right, you had to imagine that you're coming from 5 towards 4. So if you plugged in like a 4.5, you see how that would have been positive on top and it would have been negative on the bottom, but it's getting closer and closer to 4. So it's going to be 4 minus 4.001, at some point. So it'll be a still negative though, but it'll be causing that whole thing to blow up, but in the negative direction. So it's negative infinity. Okay. All right, so you try direct substitution, but when you get that issue of a 0 in the denominator, you have a vertical asymptote in this case. So you wind up trying to decide whether it's going towards positive or negative infinity. So the other version just had it going to 4 from the right. All right, now question number 20 had a piecewise. You were trying to figure out what happened as x approached 3 on one version. And the rule, you wanted the limit, let me write that correctly. You wanted the limit as x approached 3 of this function. And f of x was defined to be this piecewise function. So it had two rules with x being less than 3 or greater than 3. Okay. And so here, this mattered. Because if you're approaching 3 from the right, you're approaching from numbers bigger than 3, then this rule, this is the condition that has to be met, and it says you would use that rule. So the limit would be found by using that bottom rule, and it would turn out to be, the limit would turn out to be the 3 plus 1, which would equal 4. If you're doing the limit as 3, as you approach 3 from the left, you would have used the top rule and gotten a different number. Okay. All right, 21 involved natural log on one version. I think the other one did too. No, the natural log on one version, 21 on one version, and 23 on the other involved a natural log. You had something like this. Something where when you plugged in the -2, it gave you the natural log of 0, which you can't do. So you couldn't use direct substitution. So for this one, you're having to think about what's really going on. So that's one where you might have been good to think about which direction you're coming from. So on this version, you were approaching -2 from the right. So you had to think about here at -2, you're coming from the right, so you're coming this way. Okay, and that makes a huge difference, because if you were approaching -2 from the left, from this side right here, the limit wouldn't exist at all, because natural log isn't even defined when you're over there at -3, -4, or -3. Okay, so you're coming from the right, so the limit exists, and what this function does is that right there. Okay, and so as it approaches -2, you plug that in, you plug in like a -1.5 or something like that, just to kind of see, to play around a little bit, might help you. You're coming from this direction, so like a -1.5, or even closer, like a -1.999, and just plug it in, and find that LN button on your calculator just to test what that appears to be. Okay. And oops, and when I wrote that, I meant to say plus the 2. You're plugging in the -1.99 for the x. So when you do the natural log of something tiny like 0.001, you wind up getting a negative large number. Okay, so this right here would equal a -infinity. All right, so natural log, it does help to keep in mind domain of your functions. And so you know the domain of this function would be everything from that are greater than -2. As you come in close to -2, what happens is your function winds up approaching -infinity. Right? That was similar to number 23 on the other version. All right, then I gave you a tangent one like that as well. That was number 24 on one version, and the other version, number 23. All right, so let me take it from the other version. So if we did the limit as x approached 3 pi over 2 from the positive, and maybe we're trying to do something like 2 plus tan x, 2 plus tan x. Okay, so when you're doing this one, when you're at 3 pi over 2, you're here. The coordinates of that point are 0, -1. The sine is -1. The cosine is 0. So your tangent is undefined there. Okay. So what you got to do is think about approaching 3 pi over 2, and you're approaching it from the right, which on the unit circle would be you're approaching it that way. You're in the fourth quadrant as you get towards the 3 pi over 2. So what you want to think about is that when you're in the fourth quadrant in general, isn't it positive followed by negative? Okay. So tangent would be sine over cosine. So it's negative over positive. As you are approaching it, you're going to have a negative over a positive there. Now this 2 right here, you could separate that out and do the limit as x approaches 3 pi over 2 at 2, and you would get 2. But then when you do the limit as x approaches 3 pi over 2 from the right of this tangent x, okay, you're going to wind up getting it going towards an infinity of some sort, and you have to decide whether it's a positive or negative infinity. So you have to think about that. And so you're going to wind up having it approaching a negative infinity. So this would be negative infinity. So 2 plus negative infinity would still be negative infinity. Okay. All right, it's kind of hard to do these videos and feel like it's making sense because I'm not getting any reaction, of course, from the students. So feel free to ask me if you want me to go over it some more. I have time right after the class if you need me to. right? And then, there were some that you were asked to do. This was 24 on one version where it was a one-sided limit, but there were no trouble spots at that spot. And that might have been tricky. So if we tried 3, we don't have a trouble spot. We just get 4 over 9 minus 3, which we can simplify and get 2/3. So that one could be done using direct substitution. So that was 24 on one version and 21 on the other. Okay. All right, let me see if there's any others. Oh, and then one last one of that kind had 3 functions, 3 terms. I mean, this was 22 on one of the tests. You were looking for the limit as x approached 0, and on this one it was from the left, and you had these. Okay. And so you know that the limit as x approaches 0 from the left of 5 would be 0. Here it would be 0. But when you plug in a 0 there, you're going to get a 0 in the denominator, right? So the question is whether this last section approaches a positive or a negative infinity. So you're coming from the left, so you're coming from here. So what you're going to be plugging in for the x right there will be a negative number. So it'll be -1 over some negative number. Let's just put an example like -0.5. -0.5 in there. But it was a minus and then a -0.5, so that's going to be a positive number. But then as you go to -0.01 and -0.001, this denominator is approaching 0, but it's approaching 0 and negative while it's doing it. So that makes it positive infinity. Having a 0 in a denominator when you have a constant on top is what makes something be an infinity. But it's approaching 0, and while it's getting there, while it's headed that way, the value would have been negative. And then this had a negative here, and so you wound up ultimately with that being a positive infinity. So those took a little bit of analysis to do. You found those, I think, a little bit tricky. All right, and let me go ahead and do the last problem I want to do. 25 and 6, we're just having you use the limit process to determine the derivative. So one of them was just a polynomial, which we've done a bunch. That one you should have gotten right. 26 you should have gotten right, but it had a radical, so that made it a little harder to do. Okay, so something like this. This is 26 on both versions. One of them was x minus 5, one was x minus 3. So it gave you the formula. Okay, so you needed to do the limit as h approached 0 of f of x plus h minus f of x all over h. So you plug in the x plus h where the x was. Okay, then subtract the f of x all over h. And you're going to do the limit of that. All right, so this is the kind where you're going to have to rationalize the numerator. So I'm going to multiply top and bottom by the square root of x plus h minus 3 plus the square root of x minus 3. Do that top and bottom. Okay, now some of the mess ups had to do with changing this sign or that sign. The sign that changes was this one has to be positive. Okay, everything else needs to be the same. So then when you multiply the first 2 terms together, you get x plus h minus 3. When you do the inside 2 and the outside 2, they cancel out because one's negative square root of x minus 3 times the square root of x plus h minus 3. The other one will be positive of that, so they cancel out. Then when you do the last 2 terms here, you get minus but this is important. It's minus x minus 3 in parentheses. It's a negative times a positive would be minus, and then square root of x minus 3 times itself. All right, then in the denominator, you'd have the h times all of this mess. You're doing the limit still as h goes to 0. We haven't done that yet. So then we wind up doing some simplifying. So on top, we have x plus h minus 3 minus x plus 3 over all this. Okay. So the x and negative x cancel, negative 3 and positive 3 cancels. We have just h on top, but we see we have an h in the denominator as well that's being multiplied by something. So it's a factor. We can cancel it out. So on top we have 1. In the denominator we have this x plus h minus 3 plus the square root of x minus 3. Still haven't done the limit yet, so keep that on there. And let me make sure that's a minus. Oops, that's a minus right there. And now we're ready. We've taken care of the trouble spot. Now I can plug in the 0 using direct substitution, and I get 1 over square root of x plus 0 minus 3 plus square root of x minus 3. Okay. No limit. I don't have to write the limit. We're actually evaluating it right now and just simplifying. So that's just 2 times the square root of x minus 3. And that would be my final answer. So we were actually finding the derivative of this function. And in chapter 2, we were learning that the derivative was related to a certain limit, the limit of the difference quotient as h approached 0. We now know how to do this derivative another way. We can do the derivative of this by thinking of it as a power, setting it up so we could use the power rule, but we also need to sometimes use the chain rule, which would be involved here. You'd bring the 1/2 down in front, multiply by x minus 3, raise to subtract 1 from 1/2 and get negative 1/2 power. Then actually you need to take the derivative of the inside function. It just turns out to be 1. And so your answer turns out to be 1 over 2. And then negative exponent means you can pull it down here. And it can be written as a radical. You didn't know this when you took the test, but this is what you're learning in chapter 3. Okay. All right, so let me stop sharing on that. I'm going to post some problems for you just to do outside of class and turn in, and you can watch the video to help you.